Welcome to a screencast on the meanings of Gibbs free energy. The objectives of this screencast are to describe 3 ways to explain the meaning of Gibbs free energy and to give examples of each. So, what is the meaning of Gibbs free energy or change in Gibbs free energy? Well, there's several ways that we can look at this, and one of them is that the standard Gibbs free energy of formation, delta G sub F, is a measure of stability of a compound compared to the elements that make it up. So delta G sub F, Gibbs free energy of formation, is the reaction free energy for forming the compound from the elements in their most stable form and under standard conditions. And if we look at a graph, by example, of several compounds, iron 3 chloride, water, carbon monoxide, phosphine, nitrogen monoxide, and acetylene, we see that some have negative delta G's of formation, some have positive delta G's of formation, and there's a pretty big range of them. And for starters, we do delta G of formation of a compound as the free energy of reaction of forming the compound from its elements, and the elements have delta G's of formation of 0 if they are in their most standard or most stable form. So delta G of formation of an element in its most stable form is 0. This is sort of our baseline for comparison for the compounds. And if we have a delta G of formation for a compound that's negative, then the compound is thermodynamically stable relative to the elements. So iron 3 chloride, water, and carbon monoxide are all more stable than the elements that comprise them. And in fact, iron 3 chloride is the most stable relative to its elements, negative 334 kilojoules for its delta G of formation, than water, negative 234 kilojoules per mole, and carbon monoxide, negative 137 kilojoules per mole. All of these are more stable than their elements in terms of thermodynamics, and the magnitude of the delta G of formation is a measure of relative stability by comparison. Now, conversely, if delta G of formation for a compound is positive, that means the compound is thermodynamically unstable relative to its elements. So phosphine is a little bit unstable relative to phosphorus and hydrogen. Nitrogen monoxide is more unstable than its constituent elements, and acetylene is a pretty good fuel, partially because it's significantly unstable compared to its elements, and when it reacts, it produces or gives off a fair amount of energy. Now, a second way we can look at the meaning of Gibbs free energy, or specifically here Gibbs free energy change, is that the delta G from a process is the maximum amount of energy that's available or free to do work. And as an example, if we take sugar, sucrose, and allow it to react with potassium chlorate, it reacts very vigorously. Here's the reaction. And it has a very large delta G of reaction. It's about negative 6,700 kilojoules when 1 mole of sucrose reacts with 8 moles of potassium chlorate. Now, since this is a negative value, that means energy is given off in this process, and the 6,700 kilojoules of energy that's given off is potentially available to do some work. Now, that's the maximum that's available or free to do work. In reality, not all of that 6,700 kilojoules would be able to be transformed into usable work. Some of it's going to be lost in various ways, but this is sort of our maximum or our threshold of what is possible. And there's one more way to look at the meaning of delta G, and this is looking at it as a criterion for spontaneity, which we've seen before, and then looking at the direction of spontaneous change in terms of the direction of what happens to the free energy itself. So since delta G is the criterion for spontaneity, and specifically if we have a process that's spontaneous or a reaction that's spontaneous, the delta G for that process or reaction is a negative value. Then, if we're at constant temperature and pressure, the direction of spontaneous change corresponds to having a negative delta G value, which means that the free energy, or the G itself, must decrease. So direction of spontaneous change is direction of decreasing free energy. That's what leads to a negative delta G value for the process. And if we look at a generic reaction of reactants make products, the free energy graph for this process or for this reaction looks like this. We typically graph course of reaction on the x-axis from pure reactants on the far left to pure products on the far right. And we graph this versus free energy on the y-axis, and free energy is increasing going upward. And in this case, the reactants have a certain free energy. It's in fact higher than the free energy of the products. And the equilibrium position is somewhere in between pure reactants and pure products. And the equilibrium position corresponds to the lowest free energy that is possible for this mixture. So the equilibrium mixture is the low point of this curve. And a typical analogy that's used is it's something like a valley in between two hills of unequal height. And if we have a rock or a ball at the top of the hill and it starts rolling, it's going to roll downhill until it reaches the bottom of the valley, and that's going to be the lowest energy, most stable place for that rock to be. And whether it starts on the right-hand hill, which in this case is at a lower height, or the left-hand hill, which is at a higher height, the ball will roll downhill until it reaches the bottom of the valley, the equilibrium position. And chemical reactions are something like that. Energy, or the process, rolls downhill, so to speak, until minimum energy, lowest energy, most stable position is reached. And if we note for our sort of generic graph here, pure reactants on the left, pure products on the right, the position of equilibrium right here is where delta G is 0 and the energy, free energy itself, is at a minimum. So here's our low point. Delta G is 0. It stopped changing, at least instantaneously at that spot. We're at the low point. And if we have a closed system, reaction is going to continue until that equilibrium, that low point, is reached. And whether we start with reactants or products or anywhere in between, reaction is going to occur in a direction in which G, or free energy, decreases. So if we start with pure reactants, decreasing G is going downhill, moving from left to right in this case, until we reach equilibrium. But we could also start with pure product, so to speak, and going downhill in terms of decreasing free energy would be from right to left, and that'll continue until we reach the minimum. So reaction occurs in the direction of whatever decreases free energy until we reach the low point, or the minimum free energy value. And this is going to be the case whether the reaction that we're dealing with is product favored, in other words, delta G for the process for the reaction is negative, or reactant favored, which has a positive delta G for the reaction. And if we look at each of these individually, here is a product favored reaction. The position of equilibrium is very far over towards the products. The free energy of the reactants is much higher than the free energy of the products. And the difference between the products and the reactants, shown by this arrow, that is a change that is a negative value. The free energy decreases going from reactants to products. And do note the delta G for the reaction is the delta G from pure reactants to pure products. That's not the same as to the position of equilibrium, which is a little bit lower than either of those. And if we look at the reactant favored free energy graph, the position of equilibrium here is much closer to pure reactants, much farther to the left, and that's still the minimum. And if we compare the free energy of the reactants, which is much lower, to the free energy of the products, free energy must increase going from reactants to products. Then the delta G for this process is positive. And again, note the delta G for the reaction is from pure reactants to pure products. The minimum is a little lower than either of those. And that is it for the Meanings of Gibbs Free Energy Screencast.